Welcome to all. Myself Dr. Santhosh Singh, working as an Associate Professor in Department of Physics. Today I am going to discuss about numerical aperture in optical fiber or fiber optics. So let's start the topic. So what is numerical aperture? I already discussed in my last video lecture. The light gathering capacity. How many rays you can launch for any given optical fiber so that ray will travels from one end to another end without getting any disturbance or without coming out from the optical fiber cable. That thing, one parameter is there, so that if you know that parameter, you can tell how many wave or how many light rays you can launch. That thing is numerical aperture. So numerical aperture, the literal meaning of numerical aperture is nothing but light gathering capacity inside the given optical fiber, so that light will travels from one end to another end without disturbance and without loss, without lose their inherent property or whatever the data is contained with that rays or wave. Our information should not lost. So without any kind of loss, how many rays you can launch for a given optical fiber cable so that it can travels from one end to another end. That things will be, you can summarize or you can tell something about that with the numerical aperture value for given optical fiber. Okay. So if numerical aperture value is high, so you can say the launching is easier. You can launch more number of rays simultaneously, or okay, because the numerical aperture is nothing but sign of acceptance angle. And what is the acceptance angle? Suppose this is a given optical fiber cable, and this is the core region of given optical fiber cable. Outside of this core is cladding. So you know that the light rays which launch for traveling through the optical fiber cable network will go for successive multiple internal reflection from one end to another end. You can say this is the sending end, and you can say this is the receiver end. Okay. So how many rays you can launch for given optical fiber cable at all the surfaces so that it can go for several multiple internal reflection without merging with each other and without getting any kind of disturbance or without losing their inherent property. Inherent property means, suppose you mix some data or information with these waves, so that if they will come out from this optical fiber, there are some chances for attenuation also. So if they will come out, so obviously there is a chance so that your information or data will be leaked or lost. Okay. So for avoiding these circumstances or scenario, you have to confine yourself within the numerical aperture region. And what is the numerical aperture region? Suppose this is your acceptance cone for given optical fiber. Acceptance cones means if the ray will go through inside from this cone and strike over the core cladding interface, definitely that rays will go for total internal reflection, and that rays will never interfere with another ray, and there is also a very less chance or zero probability so that rays will also come out from this optical fiber cable. So your data will be secure, your information will be secure. Okay. So this is your acceptance cone. Okay. So now half of this angle, let's suppose this angle is theta. So half of this angle means theta by 2. So let's suppose this angle is theta by 2. Let's suppose this is 5. So this angle is known as acceptance angle. Okay. Now sine of this angle, sine theta by 2, or you can say sine phi, is known as, in a numerical term, numerical aperture. Some value will come, some numerical value will come. So you can say this is the numerical aperture. So if the value is high, means numerical aperture is high, means you can say you can launch more wave, or the launching is easier. You can launch more number of waves simultaneously, and so that wave will even not interfere, and also it will not come out from the optical fiber cable network system. Means your data will be safe, secure. So that is the concept of numerical aperture. That's why calculation of numerical aperture in optical fiber cable network communication system is very, very important. So you can calculate this in first year syllabus, or in our college BTech first year in laboratory, physics laboratory, students calculated the optical fiber cable, the given optical fiber cable numerical aperture of given optical fiber cable. Okay. So it is in our laboratory syllabus also. So they can get an idea about how to calculate the numerical aperture, and if the numerical aperture is high, you can launch more number of wave, or launching is easier. And if numerical aperture value is low, you can launch less number of wave, and even it is tough to launch. Okay, the wave, so that it will go for multiple total internal reflection. Okay, so that's overall some idea about numerical aperture. So in literal meaning, or in actual sense, what is the numerical aperture? Numerical aperture is light gathering capacity for any given optical fiber cable. So that's why it is written light gathering capacity of fiber is expressed in terms of maximum acceptance angle, and is termed as a numerical aperture. Now light gathering capacity is proportional to the acceptance angle, numerical aperture. So numerical aperture is sine of acceptance angle theta naught. So obviously Na is proportional to theta naught. So numerical aperture can be represented by sine of the acceptance angle of the fiber. Okay. Now in my last video lecture, we already calculated sine of theta naught is equal to n1 square minus n2 square upon n naught. So n naught is refractive index of air there. So n naught value is always refractive index of air. So it is 1. So sine of theta naught is equal to n1 square minus n2 square whole to the power half. Okay, so this expression I already derived in my last video lecture. I am going to define one new quantity that is known as delta, and that is fractional change in refractive index. How much refractive index is changing once you are moving from core region to cladding region, because core have some higher refractive index and cladding have some lower refractive index comparison to core. Okay, then that's why the rays will enter from denser medium to rarer medium, and once that ray will launch at the critical angle, it will reflect it back to denser medium and it will go travels without any loss. Okay, it will always be inside the core region. Okay, so for simplification, I am going to define one fractional change in refractive index in core and cladding medium, and that fractional change is represented here by delta, and delta is equal to N1 minus N2 by N1. Okay, what is N1? Refractive index of core, refractive index of cladding, and N1 again refractive index of core. So N1 minus N2 upon N1 is fractional change in refractive index of core and cladding. So based on this we can modify this formula. So from this expression, equation number 2, you can easily write N1 minus N2 is equal to N1 delta. Okay. So what is your numerical aperture? Numerical aperture is N1 square. Numerical aperture is sine of theta naught, and sine of theta naught is what? N1 square minus N2 square whole to the power half. So A square minus B square, A minus B plus A plus B. So based on that you can write here N1 minus N2, N1 plus N2 to the power half. Okay. Now here N1 minus N2 is delta N1. So you can write here N1 minus N2 is delta N1, N1 plus N2, okay, complete power half. This is what numerical aperture. Okay. Now, if we are considering N1 is nearly equal to N2, what happened? N1 is nearly equal to N2, what happened? Delta N1 and N1, if N1 is nearly equal to N2, you can write N1 is nearly equal to N2. So N1 plus N2 can be written as 2N1 or 2N2. So I am choosing N1. So this is nothing but a kind of reasoning. What is the concept behind numerical aperture? I already told. This is some mathematical exercise. So N1, NA, numerical aperture in term of fractional changes in refractive index of core and cladding, NA is equal to delta N1. Now 2N1 also, 2N1. So what you are getting? All to the power half 2 delta N1 square. So this N1 square will come out from bracket N1 under root 2 delta. So NA in term of fractional change in refractive index will be NA is equal to N1 under root 2 delta, where delta is fractional change in refractive index. So delta value is N1 minus N2 upon N1. What is N1 and N2? I already told. Refractive index of core N2, refractive index of cladding. Okay. So in term of fractional and in totality, this term N1 minus N2 upon N1 will be known as fractional change in refractive index. So in term of delta, means fractional change of refractive indices or index for any given optical fiber cable. Numerical aperture value, NA numerical aperture value is N1 multiplied by under root 2 delta. So based on that you can solve or calculate the numerical aperture also. Okay. So from equation 5, this is your given equation. It is seen that numerical aperture for any given optical fiber depends only on the refractive indices of core and cladding, and it is independent of fiber dimension, means how much your optical fiber is long or how much it having the breadth, okay, width, length, okay. So it does not depend on the numerical aperture, does not depend on the physical dimension or dimension of the given optical fiber cable. It will always or only depends on the refractive indices of core and cladding. Why? Because now you have two formula for given optical fiber cable. You have two formula for numerical aperture. The first one is what? First one is numerical aperture, NA is equal to, you can write sin theta naught, and that should be equal to N1 square minus N2 square whole to the power half. Okay, this is the first one. Now in term of fractional change of refractive indices, NA is equal to N1 to delta. So what is delta? N1 minus N2 upon N1. So in both formula, the numerical aperture is only depend on the refractive indices of core and cladding. Okay. No other dimension term of given optical fiber cable are considered optical fiber cable not involved in the formula of numerical aperture. So you can say that the numerical aperture means light gathering capacity of given optical fiber cable is only depend on the refractive indices of core and cladding. Okay. Now if the ray is traveling, if there are multiple lawns, so suppose if rays are traveling through the optical fiber cable, there are the chances so that some losses will occur. Okay. So that losses in term of communication system, that losses is known as attenuation. Okay, attenuation. So attenuation is the loss of power suffered by optical signal as it propagates through the fiber. It is also called fiber loss. Okay, loss in fiber or attenuation in fiber. Signal attenuation means whatever the attenuation happen or occur is defined as the ratio of input power, what power you are sending from this end, Pi, into the fiber to the output optical power received, means Pi upon P naught. Suppose you are sending Pi power and you are receiving here P naught power. So ratio of Pi upon Po is considered as signal attenuation. Now the attenuation coefficient of the signal per unit length is given as alpha. Alpha is attenuation coefficient per unit length. So actually alpha is equal to 10 log of Pi upon P naught, attenuation coefficient. But if you are considering attenuation coefficient per unit length, so you have to divide this alpha by length. Okay. So it is the attenuation coefficient of the given optical fiber cable for per unit length. Okay. Where L is the length of the fiber. The mechanism through which the attenuation take place in the given optical fiber. What are the causes so that the attenuation will occur? Is absorption loss, means your rays will absorb by the material of optical fiber. Scattering, there are the chances so that your rays will scattered by the molecules or atoms which are available inside the optical fiber, and bending loss. Suppose your optical fiber cable have some sudden or discontinuous break or bend, so there are such type of losses also occur. Then micro bending and waveguide losses is also. So these are four categories so that by which the attenuation or losses can occur through any optical fiber cable. Now application of optical fiber. So your optical fiber cable can be used in sensor devices. So also in power transmission. Okay. So obviously it is well known fact that the optical fiber cable will used in power transmission. Okay. Now in telecommunication, and the most important in medical application. So with the help of optical fiber cable, you can see the inner picture of any person, inner picture of body of any sick person or any patient where the diseases are going present. Okay, and you can, for getting the clear view or picture, you can easily diagnose what are disease there and what is the best possible medication for that disease. So all of these application of optical fiber. So thank you.
Like, share and subscribe. Hit the bell icon for more updates.